Hello everyone, today's topic is an introduction to eigenvectors and eigenvalues, material from chapter 5.1. So we're into chapter 5 now, and full disclosure, this is kind of where I think the class gets most interesting. We're kind of reaping the rewards for what we've been studying so far, and we'll see, in terms of both theory and applications, I think this is where linear algebra really comes to life in context of eigenvectors and eigenvalues. So maybe just the idea, I'll give you a rough idea, a bird's eye view here, is that we want to choose, or say find, a basis for Rn, right? Bases are something that we've been talking about. You want to choose or find a basis for Rn that kind of works well for a given matrix, let's say square matrix n by n. Okay, so that's kind of a very loose statement here, but we'll see that we'll make this more precise as we move forward. Let me give you an example. So e.g., suppose A is the matrix 3, 1, minus 2, 0, a 2 by 2 matrix. And let's take the vector v, 2, 1. Let's take the vector u to be minus 1, 1. Let's compute A times v. Okay, so it's a matrix times a vector, so we're going to get another 2 by 2 vector back. What do we get here? Well, let's see. So this is 6 minus 2, it's 4, and then 2 minus 0 is 4, 2. So notice that I took A, I multiplied it by the vector 2, 1, and I got 4, 2. So this is actually twice times 4, 1. So the result of, so what this is saying is that A times V is twice, is twice the vector v. So A kind of stretches, stretches v by 2, I guess. But in particular, the image of v under this transformation given by A is in the line spanned by, so let me just draw a picture here. So if we have v is 1, 2, 1, right, here's v. What's AV? It's just twice that. So AV was, in particular, it's in the line that was determined by V to begin with. It stays in that line determined by V. Maybe just to calculate what's A times U, that's 3, 1, minus 2, 0 times, what was U? U was minus 1, 1. So this gives you, let's see, minus 3, minus 2 is minus 5, right? And then this is a minus 1. So this is saying that, this is not equal to some multiple, say, k times minus 1, 1. So, this is a different situation where I take a vector minus 1, 1, right? This was u, and I get minus 5, 1, 2, 3, 4, 5, minus 1. So the image now is not in that line determined by u. And we'll see that this is kind of a good situation that that a vector stays in the line, when I apply A to it, it stays in the line determined by V. This is going to be not so nice. I mean, this is a more typical situation. If you just write down a random matrix times a vector, you're not going to get something that's staying in that line. But we'll see how this situation is desirable. Okay, so that leads us to our first kind of important definition. So definition. An eigenvector of an n by n matrix A. So I should say that all the matrices here for the next couple lectures will be n by n squared. So we've got a square matrix. An eigenvector of such a matrix is a non-zero vector, V, say, satisfying what we just saw, that when I take A times V, I get back lambda times V for some real number, lambda, right? So we saw before that when I take A times the vector in the first example, I got a scalar multiple of what I started with. So that's an eigenvector. This number lambda is called an eigenvalue. So this number here that is doing the stretching. And just terminology, if AV equals lambda V, we say that V is an eigenvector with eigenvalue lambda. Okay? And again, maybe just one more example. We've already seen one, but just one more time. E.g., if A is, I don't know, 1, 5, 6, 2, and I'll ask, is U equal, let's say, 3 minus 2, is this an eigenvector? For A. So just want to point out that this is an easy thing to ask. If I come to you, or someone on the street comes to you with a vector and they say, is this an eigenvector for your matrix? You just compute. So just compute. Just is, well, you've got to do a matrix times vector computation. So what is A times U? It's 1, 6, 5, 2 times 3 minus 2. What do I get here? This is 3 minus 12, which is minus 9. And then I get 15 minus 4, which is 11. All right, so 3 minus 12, yeah, that looks good. This is 15 minus 4, which is 11. So this is not an eigenvalue because, not an eigenvector because, no, since A times U, which is minus 9, 11, is not a multiple of 3 minus 2. What about, just to show you guys another example, what about V equals 6 minus 5? Well, let's take A times V. That's going to be 1, 5, 6, 2 times 6 minus 5, which is, let's see, so 6 minus 30, which is minus 24. And then this is 30 minus 10, which is 20. So look at this. In this case, we note that minus 24, 20 indeed is what? Minus 4 times 6 minus 5. So this was minus 4, so this is AV is minus 4 times V. So this implies that V is an eigenvector with, what's the eigenvalue? Well, it's the thing that's, doing the scaling here. So it's going to be lambda equals minus 4. Okay, so that's the basic definition. I mean, again, relatively simple definition, but we'll see that we get a lot of mileage out of it. Let me do maybe one more perspective on this. So again, let's let A equal 1, 5, 6, 2. And now what I want to do is change perspective a little bit. I want you to show, or I want us to show, that the number lambda equals 7, right, is an eigenvalue. And then I want you to find a corresponding eigenvector. Okay, so this example is going to be nice because it's actually going to give us a kind of recipe for finding things. So I should say that, in the previous examples, I always gave you a vector and I said, check if this is an eigenvector, which we saw as just a computation. But here what I'm saying is, okay, I'm giving you an eigenvalue, right? This number that's supposed to do the scaling, and I'm asking, cook up the eigenvector for me. Okay, so what are we trying to do here? So suppose we have an eigenvector with eigenvalue 7. What that's saying is that A times V equals 7 times V, right? Because this is saying you would, if you have this case, then you have a vector V that is an eigenvector with eigenvalue 7. Now what this is implying, let's subtract 7V from both sides. So what you get is AV minus 7V equals the 0 vector just by subtracting 7V on both sides. And what this is saying is that, well, you've got a V here that I can factor out in some sense. So I'm going to write this as something times V equals 0. Now, I want to write A, and you kind of want to write 7 here, but notice that this doesn't make sense because A is a, well, n by n matrix or a 2 by 2 matrix here, and 7 is a number. So I can't write A minus 7, but I want to know what is the matrix that's, doing this multiplication by 7. So what I want to have here is a matrix in this part, right, in the second part of the subtraction. I want a matrix that has the result of multiplying by 7. So what I'll do is take 7 times I, right? So in this case, it would be the I2, the 2 by 2 identity matrix. But you notice that 7 times I times the vector is the same as 7v. So when I'm factoring out a 7, what I'm really factoring out is a 7i, because I want this to make sense as a matrix minus a matrix, okay? But notice now that, again, we're looking for v. So now we want to solve for v. But what is this? This is a, note that a minus 7i is just a matrix, a square matrix, in this case 2 by 2. And this is the unknown. So what we're really doing is we're solving a homogeneous, or the homogeneous system, a minus 7i x equals 0. Right, again, this is just a coefficient matrix, if you like. Okay, and so one more time, we've seen this over and over, that we're, seemingly we're talking about a new concept, but it all boils down to solving a system. Okay, so let's do that here. In this example, what is a minus 7i? Well, a is up there, it's 1, 5, 6, 2, and 7i is the, again, 7 times the identity, so it's 7, 7 on the diagonals. And so what you get, the coefficient matrix will be, let's see, so this is coordinate-wise subtraction. This is minus 6, 0, 5, minus 5, if I did things right. No, that should be a 6 here, okay, right? Looked a little funny. Okay, and then let's solve. So the system becomes, well, minus 6, 6, 5, minus 5, and I augment with 0, 0, right? So I could have left that column out because it's homogeneous, but just to emphasize that we have a system here. And let's row reduce this thing. Well, I'm scaling this by minus 1, 6. This becomes 1 minus 1. This will clear, right, because it's just a multiple of the first row. And this is my reduced row echelon form. And this has general solution, right? You guys know how to do this. The general solution for this guy is, well, there's one free variable, x2. And so the general solution, turns out, will be x2 times 1, 1. Okay? Well, what did we just say? Okay, so what do we do? Don't lose track of what we're doing here, right? We're solving for something that's an eigenvector with eigenvalue 7. It turns out that any multiple of 1, 1 will work. So take v to be any multiple of 1, 1, so x2, 1, 1. So e.g., let's just take v to be 1, 1. And maybe just to finish off here, we can now check that that's going to work. In other words, let's check that if I take a times 1, 1, well, remember, don't forget that a was 1, 5, 6, 2 times 1, 1. What do I get here? I get 1 times 1 is 1 plus 6 is 7, 5 plus 2 is 7. So indeed, that's 7 times 1, 1, right? So what this is saying, this is a times v equals 7 times v. We got what we wanted. We got an eigenvector with eigenvalue 7. Okay, so that's the, more or less, actually, this is almost a complete description of kind of what we're going to be talking about. Next time we'll talk about the general strategy for finding eigenvectors, eigenvalues, and we'll do a bit bigger examples. See you then.